Hey everybody, my name is Frank, and this is the Python Programming video log. Today, I'll show you how to do axis-aligned and non-axis-aligned collision detection and response between arbitrary polygons and flat surfaces. If you want to make a physics-based game, this is a great place to start. In part 1 of this video, I'm going to essentially show you how to get the axis-aligned bounding box or hitbox of a polygon and how to use it to do collision detection with the edges of the world. Then in part 2, I'm going to show you how to get the non-axis aligned bounding box of a polygon in order to do collision with the tilting bottom boundary you see on the screen. Be sure to check out the source code for this video on my GitHub page as well as the working example. You can find both links in the description below. As always, leave a like if you learned something, and of course comment if you have any questions or helpful things you would like to share. So first of all, what is an axis aligned bounding box? What is a hitbox for this polygon? So this triangle right here has a rectangular hitbox. You can see that pretty clearly. I have it drawn around there. So why we call it axis aligned is because the sides of the hitbox line up perfectly with the axes in a Cartesian coordinate system. They're perfectly right and left and perfectly up and down, perfectly straight sides, and it's really easy to test collision that way with rectangles, and that's exactly what we're doing here. We're just testing to see if they're overlapping these perfectly up and down and left and right sides of our world. So we use an axis aligned bounding box to do that because that's the easiest way to do it. So how do we actually check to see which points make up the edge points in the polygon of our hitbox? Well, that's pretty simple. Let's say we're checking for the top. All we have to do is get the topmost point or the farthest point up in our polygon, and the y value of that point is going to be the top of our hitbox. So just take a look at the points here in this polygon. You can see whenever a point reaches the top, whenever it's higher than the other 2 points, it becomes the top of our hitbox, the y value of it, that is. So let's take a look at this little chart I made here to better understand what we're looking at here. So this is going to be the x-axis, this is going to be the y-axis, and in JavaScript, y decreases as you go up. In regular Cartesian coordinate system, y increases as you go up and it decreases as you go down. So y would be negative and y would be positive, and x stays the same. So x is positive to the right, x is negative to the left. In JavaScript, y is negative as you go up and y is positive as you go down. So what we do to get this is basically we just loop through all of our points and we check to see which one has the lowest y value. So we're just going to go ahead and we're going to start here. We're going to go, does this have the lowest y value? No. Okay, we're going to loop to the next one. Does this have the lowest y value? Well, compared to this one, it's the same. So I'm not really sure yet, but we're keeping track of it. Does this have the lowest y value? Yes. Compared to these two, it does. So we're actually going to take that y value and store it. Does this one have the lowest y value? Well, it's the same as the last one, so not really. Then we're out of stuff to loop through, but we have the lowest y value recorded, so then we can test to see if that y value is less than the top of our world, and if it is, we can go ahead and do collision, and we could use that y value for the top of our hitbox. So that's how you get the top of your hitbox, and it's the same kind of thing to get the right, left, and bottom sides of the hitbox as well. Now that we've visualized what we're doing here, looping through the points and getting the point that's farthest along in a given direction, let's take a look at the actual code that does this. So we're going to use this example right here, and this is the getRight function. So this function here is part of the Polygon class's prototype. It's a method in the prototype, and it gets the rightmost value, the rightmost x coordinate of all the points in a given polygon. So let's use this polygon right here. We're going to test to see what the farthest right point is, or what the x value of the farthest right point is. So we start out by getting a vertex. We're going to get the vertex at position 0 in our vertices array. Let's just say it's this one here. Let's say this is position 0, this is 1, this is 2, and this is 3. So we're going to start out at position 0, which is this guy right here. We're going to store its x position in this variable called right, and then we're going to go ahead and loop through the rest. I loop backwards, so we're going to start with the last vertex in the vertices array. So it's going to be this one right here because, 0, 1, 2, 3. So we're going to go to 3, and we're going to get that vertex. We're going to test to see is this vertex's x value greater than the value we stored for right, which was this vertex's x value. Well, they're exactly the same, so we just continue the loop and we go to the next one. we're going to go to this one. We're going to check to see, is the x value of this vertex greater than the value we have stored for right? It is, because it's farther along the x-axis in this direction. It has a greater value. So now we make right equal to the x value of this vertex. Then finally we loop to this vertex at position 1, and we stop the loop at 1. Say we're looping from the last vertex, the last index, to a value greater than 0, because we already did 0 right here. We already checked 0 right here, so we don't need to check it again. So we're going to say loop from the end to a value or an index that's greater than 0. What's greater than 0 here? 1. So we finally stop at the vertex at position 1. We check its x value. It's the same as this, so we don't do anything, but we still have right, and right stores the farthest rightmost value, the farthest rightmost x value of all the points in this polygon, and that's how we can get the right side of our hitbox for this polygon. Now it's the same for all the other functions: get right, get left, get top. Here's get top. It's the same exact setup. It looks pretty much exactly the same. All we're doing is testing to see what the highest, or actually the lowest, y value is in our polygon. So that's the code for it. Now that we know how to get the hitbox, we looked at the code, we looked at it visually, and we know how to get the hitbox of our polygon, let's take a look at actually implementing collision. So I have this function here called collide rectangular container. It takes a polygon object. It has the left, right, and top coordinates of our container, in this case the world. So left, right, and top are going to refer to the left, right, and top sides of the world here. Basically, I'm just going to get each side of the hitbox. So let's take a look at this hitbox here. Polygon left, right, and top are going to be left, right, and top of that hitbox. So then it's just a simple matter of basic collision detection. We're going to say, is the left side of the hitbox to the left of the left side of our boundary? If it is, then we run this code, and that code resolves collision. Set position plus is just going to take an x value and a y value and add that on to the current position of our polygon. It's going to update all the points. It's going to update the registration point that they rotate around. So that's pretty simple. We're just taking this value and adding it to our position on the x-axis to push it out of collision with the left boundary. This right here reverses the direction of the polygon. So the polygons are moving in a direction, and that direction is recorded in radians, which are just rotational coordinates. So what I'm doing here is I'm using math.sine and math.cosine to get the y and the x Cartesian coordinates from the rotational direction coordinates in radians of the polygon, and then I'm converting those back after I modify them with math.atand2. So what I'm doing is I'm getting the y velocity of my polygon here with math.sine. I'm extracting the y velocity from the radian coordinates, the polar coordinates of polygon.direction. I'm extracting the x coordinate, the x Cartesian coordinate from the polygon direction, and then I'm modifying the x direction of my polygon because I'm colliding with the left side. I want to invert the x direction, multiply it by -1, so that's exactly what I do. I get the x coordinate, I multiply it by -1, and then I put these values back into polar coordinates with math.atand2. So I'm just getting the Cartesian coordinates, and I'm modifying them a little bit, and then I'm putting them back into polar coordinates with math.atand2. And it's the same kind of deal for each one of these, and that's implementation. Now let's try to visualize non-axis line bounding boxes. It's not going to look like this. It's not going to be perfectly square. In fact, we're not even really going to get the non-axis line bounding box. We kind of are, but like the axis line, we're just going to get points on the edge of that axis line bounding box. We could draw one if we really wanted to, but that's a lot of work, and we don't actually really need to ever have the full thing, just different points on it. So what would we use it for? We'll use it for this down here, this big line segment. It's a line segment that goes from here all the way to here, and I filled in the bottom side of it with blue, so it looks like a big polygon, but really we're just colliding these polygons with this top line segment right here. And just like we do collision with these other axis aligned boundaries, the top, the left, and the right, we're going to do the same thing for this. It's just that this is tilted. It's the same basic math, we just have to adjust it for that tilt. So how do we think about this differently because of the tilt? So really what we're testing when we do a collision with the left side isn't, you know, the left up and down side. We're actually testing to see if a point is farther left on that x-axis. That x-axis is axis aligned. It has no y value. It's just x left and right, no up and down. So we're just testing to see if a point is farther past this boundary on the x-axis. Well, for this, we're going to do the same kind of thing, except the axis is tilted. So we're going to test along an axis that runs perpendicular to this big long line segment here. We're going to test to see if a point has gone past this point on this tilted axis. And I'm trying to go 90 degrees to this line. We want an axis that's perpendicular to this, but you know, it's hard to show you just like this. So I have this chart here that we can use to hopefully help visualize it. So imagine this is the perpendicular line to that big tilted blue thing on the bottom of the screen from before. So this is going to be that axis that we're testing against. So to get the farthest point visually, we can see we just have to loop through these points and get the one that falls farthest along this axis. So if we were going to test for the point, in this case, we're testing for the point that's closest to the top. So let's say we have a big line up here that is a big tilted top boundary instead of that bottom boundary. In retrospect, I guess I should have made this a little different, but that's okay. We have our top boundary up here. It's a big line segment, and we're trying to get the point that's closest to that on this perpendicular axis to the line segment itself. So we just loop through each one of these points. Let's start here. And we test to see, is the dot product greater than any other of these points in this direction? So when we were testing this over here, it was simple. We just tested to see, is the y value less than the y values of these other points in the polygon? And if it is, then we're going to use that y value, and that's going to be the least amount of y value is going to be the y value we use to get the top. With this, instead of using a y value or an x value in the case over here, we're going to use dot product, because dot product is directly equated to or directly related to the distance that these points are along this perpendicular vector to our line segment. So instead of using y or x, we're going to use dot product. And it's the same basic concept. So we're going to loop through. And by the way, the formula for dot product is right here. It's just point.x times vector.x. So if this is a vector, we're just going to multiply this.x times this.x plus this.y times this.y. And that's going to be our dot product. So it's really not hard to get the dot product. But anyway, we're going to loop through our points. Let's start with this one. We're going to get the dot product between this point and this line. So point.x times vector.x plus point.y times vector.y. That's going to be our dot product. We're going to keep track of it. We're going to iterate over to this point. Is the dot product of this point with this vector greater than the dot product of this point with this vector? No, it's the same. So we're going to keep looping. Then we get the dot product of this point, and we can see that clearly the dot product, which is directly related to this point that we end up on by drawing a perpendicular line from the vector to this point, the dot product is going to be greater for this point than it was for this point or this point down here. And we can see that just by looking at where they would end up if we projected them onto this vector here. So we know that this point is farther than this point. So we take the dot product of this point and we store the y value, or the x and y value of this point. So then we move on to here and we test, no, the dot product isn't as big as the dot product for this point was, so we exit and we just use this point. This is the point farthest along this vector, and this is what we're going to have to use to collide with a line segment up here. And that's a pretty good way to visualize it, I think. Now let's take a look at the code that actually determines which of these points is farthest along in this direction here. So we're going to look at this function. It's the getFarthestPoint method of the Polygon prototype. It takes a vector x and a vector y coordinate. So basically this is the vector we're going to be using for this example here, and its x and y value, whatever those may be, are what we're going to plug into this function here. So just like when we were looping through this guy over here, we're going to do the same thing for this guy right here. We're just going to loop through each one of the points, get the dot product, and test to see which dot product with which point is greatest, and we're going to return the point with the greatest dot product. So we start out by getting a vertex. We're going to start with vertex 0. So let's say this is vertex 0 right here. This is 1, this is 2, this is 3. We're going to first get the dot product. Now the dot product, like I said, is just vertex x or point dot x times vector dot x plus vertex or point dot y times vector dot y. So we have this right here. Dot product equals our vertex dot x times vector dot x plus the vertex dot y times vector dot y. The farthest point we're going to store as this point, because this so far is, as far as we know, it is the farthest point. We haven't checked any other points. We don't know if any other exist as far as this algorithm is concerned. So we're going to store this, and we're going to store our dot product in this variable right here. Then we're going to start looping. I loop backwards, so we're going to start out at position 3 because we have 0, 1, 2, 3, and we're going to loop all the way down to 1 because we don't need to loop over 0. We just checked it. So we start out at position 3. We get the vertex at position 3. That's this right here. We're going to get the test dot product. Test dot product is just going to be a dot product, and we need to have a separate variable for it because we don't want to overwrite the current dot product that we're storing. And we just test to see, is the test dot product greater than the current dot product we have stored for this guy here. So is the dot product of this greater than the dot product of this? Well, if we look at our chart, we can see that no, it's not. The dot product for this is lower along this vector than the dot product for this, which is up here. So this, along this vector in this direction, is less than this. So we're just going to break out of the loop, and well, we're not going to break out of it, but we're going to go to the next iteration of the loop. We're going to go to this guy here and test the dot product. So our current dot product is this right here. It's related to this right here, or relative to, rather. The dot product value is just a scalar. This would be an actual point, but it's directly related to this point here. So we test to see, is the dot product of this greater than the dot product of this? Well, it's actually exactly the same. So we just do nothing, and we go to the next point in the loop, and we test to see, is the dot product of this greater than the dot product of this? Why, yes, it is. We can see that it is by looking right here. It's greater, so we store this point, and then we're at a point. So we break out of the loop, and we return this point here at the bottom of our function. And that's the code to get the farthest point in a given direction using the dot product. So now that we know how to get the farthest point in a polygon along a certain direction, arbitrary direction, let's go ahead and see how we do collision with that farthest point. So I've made this graph for that. C is going to be the farthest point along in our polygon along a given direction, and AB is going to be our line segment. So just to refresh, we have our line segment from point 0 to point 1 here, this big tilting line segment, and we have our polygons, and we have our right hand normal, our perpendicular collision axis to this line segment, going from here down, essentially. Basically, we're going to take the vector of this line segment and we're going to rotate it 90 degrees to the right, and that's going to give us a vector that points straight down at a right angle to this line segment. And we're going to test in that direction to get the lowest point on each one of these polygons to do collision. And that lowest point towards that direction is going to be C. So in this example right here, given that this is point 0 and this is point 1 of our line segment, we don't actually have a collision because C would be to the left of our line segment. But if C was over here to the right, we would have a collision. We'll talk about that a little bit later. But this is the setup. We're trying to find CD because CD is our penetration vector. Now if the dot product of CD is the same as the dot product of, or not negative, but if it's positive and the dot product of our AB normal vector is positive, then we don't have a collision. So we don't have a collision here because this vector is going this direction and the normal of AB is going this direction, so this is no collision. If CD was negative, however, the dot product of CD was negative compared to the dot product of the right-hand normal of AB, then we would have a collision. C would be over here somewhere, and we could use C to D for our penetration depth, and we would just have to move our polygon by C by the amount of that penetration depth to resolve our collision. So that's why being able to find CD is so very useful. So let's take a look at how we can find CD, given that we know point A and point B on our line segment, and the distance from C to A, and also we have C. So we have C, we have AB, and we have CA. So those are givens. So we're going to go ahead and look at this. AB, we have that, and by the way, these are the vectors here. So if we take a look at this example here, and we work out vector CD and vector AB and vector CA, all of those could be graphed and look just like this. So this is our vector graph right here that we're going to refer to. So we're just going to work through this. We know AB is this right here. It's 8 and -8. It goes over to the right and up to the top. CA goes straight down. We've got CA here. It goes straight down to A. Then we've got CD. We don't know what CD is, but we know just by looking at it that this is CD. And if we really wanted to figure it out, we could just count it out. We could go 1, 2, 3, 4, 5.5, and 1, 2, 3, 4, 5.5. So we know that CD is 5.5 and 5.5, but we didn't actually do any math to get there. We're just eyeing it up. So let's figure out how to solve for CD here. Another thing that's crucial that we also know is that the dot product of CD and AB, which is this equation right here, is going to be equal to 0. We don't know the x and y values of CD yet, but we do know AB has the x values of 8, or the x value of 8 and the y value of -8. But we do know that the dot product of those is going to be equal to 0. And the reason for that is because they're perpendicular. So if you do the dot product of CD and it's perfectly perpendicular to AB, we're going to get 0. And to prove that, I can show you that right here. Let's go ahead and go here and hit dot product. The dot product of two perpendicular vectors have a dot product that's equal to 0. These are two perpendicular vectors that are at 90 degrees. Dot product is 0. So we know that to be a verifiable fact. Let me go back to cross product there. I'm going to use that a little bit later to show you something cool. So we know that dot product of CD and AB is going to be equal to 0. Let's work through the rest of this to figure out what CD is. So to find CD, use the following equation. This is just something you're going to have to memorize. But basically, the vector CA plus factor X, and you don't have to call it X, you can call it whatever you want, but this is just some unknown factor that we're going to figure out what CD actually is. So we have CD, vector CD equals CA plus factor X times vector AB. And we could break that down into the X and Y components, and we get CD.X equals CA.X plus factor times AB.X. And for Y, we have CA.Y plus factor times AB.Y. So these are what we're going to use. These two equations are going to be used to find X and Y. Now, we have to figure this out by plugging these equations into this dot product formula, and that's why it's so great to know this dot product formula, and we know that CD.AB is equal to 0, because we can substitute X and Y into this formula right here to figure out X. So to solve for X and Y, first find factor X by substituting the equations for X and Y into dot product CDAB. So what that looks like is this right here. We're going to take literally this right here for X, and we're going to replace this X value with it. And we're going to take this right here for Y and replace this Y value, and we get this big long equation, which is equal to 0. So we're going to simplify this down, and I'll show you all the variables and how it looks in the code in just a moment, but we're going to simplify all this down to find X. And after simplifying, we can find that X equals 88 divided by 128. And I encourage you to actually write this down and do this very thing so you can see the math actually working, and then try a couple of your own. Draw a couple of these out and actually try this on it to see it work. So finally, once we know the factor X equals 88 divided by 128, we're going to solve for X and Y. So X and Y, those equations are right here. We have 0 plus factor X, which we now know is 88 divided by 128. We multiply that by 8, and we get 5.5. Same thing for Y. We do 11 times 80, or 11 plus 88 divided by 128 times -8, which is AB.Y for this formula right here, or equation right here, equals 5.5. And we can verify that because we know just by looking at it, we can count out 1, 2, 3, 4, 5.5, and that's what we get. 1, 2, 3, 4, 5.5, and that's what we get. So we have now found CD. So now let's take a look at the code that actually does this for us in the program. So that's right here. It's a function called collide bottom boundary. It takes a polygon as an argument. The first thing we're going to do, and I kept the naming convention pretty much the same, so you can see what all this stuff is relative to this this example graph right here. So AB is going to be the vector of our line segment. So this line segment right here is going to be this big line segment right here from point 0 to point 1. So AB is going to be our line segment. ABN is going to be our normal. So that normal is going to be this line segment just rotated 90 degrees to the right. So it's going to be this right here. And interestingly, it's parallel to CD. So this is our vector for AB. If we were to rotate this 90 degrees to the right, it would be directly parallel to this CD right here. So ABN is just going to be a normal vector pointing to the right of AB. Doesn't really matter what size it is. Then we're going to get C. Now we know how to get C because we know how to get the farthest point along a given direction in our polygon. C is going to be the point in the polygon that's farthest along ABN. So we're just going to say polygon.getFarthestPoint, abn.x, abn.y, and it's going to give us the farthest point in our polygon along that right-hand normal of AB. Then we're going to get CA. That's no problem. We know what C is now because we got that farthest point. So we just have to get the farthest point, or not the farthest point, but get the vector between our farthest point in the polygon and just a point in our line segment. I'm using point 0, and we get CA. Now we test for penetration. Is there penetration from C past line segment AB? And we can use get cross product of CA on AB to do that. So let's take a look at this right here. Let's say, what is CA? CA is going to be vector 0. Let me hit cross product here. This is going to be, I believe, CA, and this is going to be AB. So we know that we have, actually it's going to be the opposite. It's going to be like this. So this right here is going to be AB, and this right here is going to be CA. So let's take a look. I think I got it set up about right. Let's take a look here. This is going to be CA, or this right here is going to be CA, and this right here is going to be AB. So we have AB up and to the right a little bit, and CA is pointing straight down. So AB is going to be up and to the right a little bit, and CA is going to be pointing straight down. So if CA.get cross product AB is greater than 0, we know that we have a collision and we could run the code inside. So let's take a look at our example program. We know the cross product here is less than 0. And we know that this doesn't have a collision because our lowest point on our polygon is not, the cross product of CA with AB is not greater than 0. It's actually negative. So we know that point C is not on the right side of the line segment AB, and if it's not on the right side of the line segment AB, you can see by looking here, if it's not on the right side, which is this side of this line segment, we don't have a collision. So all these lowest points, all these C points, these lowest points on these polygons are not below this line right now, and we don't have a collision. All right, so we know that if we were on this side, we would have a collision. So let's just imagine that point C is actually now over on this side for all intensive purposes. Now we need to solve for CD. So CD would be from here to here. If we do have a collision, we need to solve for the factor. So the factor, this factor x, this unknown factor x, we can get with this formula here. CA plus x times AB. And that's going to give us this, and we can plug it into this dot product formula. So this is actually, I meant to say this is the formula we're going to work out right here. And what this works out to be is negative AB dot x. If you actually work this out a little bit, you get this form here. You get negative AB dot x times CA dot x minus AB dot y times CA dot y, and you divide all of that by AB dot x squared plus AB dot y squared. and that's going to give you factor x. So now we can use that factor x, we can plug it back into these x and y component equations for CD, and we could just simply solve to get what CD is, which, if you remember, is 5.5. So now we know our penetration vector. For this example, it's 5.5, but say it was over here, maybe it would be, negative 5.5, or the opposite. So it would be negative 5.5 and negative 5.5, and it would be facing up this direction here. We would know that that's the amount that we have to move our shape back by to get out of penetration with AB, or the right side of AB. So let's say CD is out here. It goes from this right here up to here. We know we have to move our lowest point on our shape from here all the way back up to here to set it back out of collision with the right side of the line segment AB. And that's exactly what we do. Once we figure out what CD is by creating that vector from this here, using the equation and substituting in the value we have for factor into here, we can figure out what the CD, the displacement vector to resolve our collision is, and then we can just go ahead and add that vector's coordinates to our polygon with polygon.setPositionPlus. And all setPositionPlus does is add the x and y value you hand in to the position of the polygon, and it just updates all the points. So that's how it's done. This is how you resolve collision if a point goes beyond a line. This here is actually how you get the shortest distance as a vector between a given point and a given line segment. So pretty useful stuff, and that's how it's done. So I forgot to mention a couple formulas, a couple functions that we use in the program that are pretty important. We don't actually use 2 left normal, but it's still important to know how to calculate a normal. We use 2 right normal. So basically this is going to take a vector. We were using vector AB, so this right here, and we were getting the right hand normal to use with getting the farthest point along that normal in our polygons to do collision with the line segment AB. So this is how we calculate a normal. Basically you just take the x and y components of the vector and you switch them around. So you set the x component equal to the y, and you set the y component equal to the x, and you just basically take your vector and you rotate it 90 degrees either to the right or 90 degrees to the left. So same thing. One thing to note is we negate one of those values. So if we're going to do the left hand normal, so if we were going to take AB rather, if we were going to take AB and rotate it to the left 90 degrees, we would set its x value equal to its y value and its y value equal to negative its original x value. If we were going to rotate to the right 90 degrees, we would be doing this right here, and we would be taking its x value and setting it equal to negative its y value, and then setting its y value equal to its original x value to get AB to rotate 90 degrees to the right. Also, we have cross product up here. Basically, it's just this format. So you do the x value of whatever vector you're using multiplied by the y value of the parameter vector, the vector you're getting the cross product with, and then you subtract the y value of the vector you're getting the cross product with, and then multiply that by the x value of that other vector you're getting the cross product with. So these are the 3 functions that I forgot to mention, and they are pretty important to doing this stuff. Anyway, I hope you guys enjoyed the video. If you did, go ahead and leave a like or a comment or something. That'd be great. And I'll see you guys in the next video.